Good afternoon, everyone. So organizers asked me to talk about size, structure, and morphology of galaxies in the first billion years from the modeling perspective. And that's what I'm going to try to do to the extent possible in 25 minutes. So I had to make choices that, of course, reflect my personal interest. But I meant it as a conversation starter, as discussion starter. So I hope that this will generate discussion afterwards. And I also wanted to convey something that we learned in the few weeks leading to this conference during this workshop. So some things that I'm going to show you were results of discussion that happened here, and I wanted to share you with those of you who weren't here, the excitement and sort of the questions that have been raised. So not to insult your intelligence, but if we look at integrated properties, and they're listed here, and I'm sure this is very redundant for this audience, the integrated properties of high redshift galaxies, redshift galaxies, they all, I would say, look pretty normal. If we look at stellar masses, metallicity, and star formation rates, it's nothing that we have not seen at redshift 0, right, or some intermediate redshift. So if you think about those things as only, and this is often what we do, these galaxies are not that unusual. They have typical stellar masses, typical metallicities, typical star formation rates, but that's when we start looking at their sizes and we start looking at their structure, we start looking at their morphologies, and when unusual things happen, right? Like the sizes tend to be quite small, the morphologies tend to be clumpy, very irregular, but at the same time we see disks. Sometimes they are very large disks, as Harris told us this morning. So that's where surprises lie, and that's luckily is the subject of my talk. So hopefully it will be interesting. So sizes, I'll start with sizes, right? And there are many studies who did this, which did this observationally. And to set the stage for models, I need to talk about observations. So this is half-light radius in UV as a function of stellar mass from the work by Morishita et al. But again, there are several studies of this kind that I try to give credit here. And you see that the sizes are correlated positively with stellar mass, although you may question the strength of this correlation. It looks more like a cloud, but at least there is some sort of a relation that apparently indicates a slope. That's what they derive from this paper. And we will hear from Arjun van der Velde later in this session about how difficult it is to measure these sizes and all the pitfalls and biases that are present. But I think it's pretty non-controversial to say that galaxies above redshift 5 are smaller than at redshift 0 and even smaller than at redshift 3. And you can see this by comparing this median here with the dashed line shown there, which is a median for 2.7 star-forming galaxies, right? So there's a factor of several difference. And this is quantified here where the effective radius is normalized by the stellar mass, by this best fit relation. And you can see sizes at redshift 2.7 from the study, the Arjun study, extending, if you extend them to galaxies beyond redshift 5, there's about 1 plus z, inverse 1 plus z decrease in the half-light radius, right? Now, so this is what I've meant by galaxies being smaller on average. And of course, this is exactly what's expected because our basic expectation for what should be happening to sizes is set by classical models of sizes of galaxies that assume that the size is set by specific angular momentum, which galaxy acquired during collapse due to torques from surrounding structures. And in these models, without going into too much detail, the sizes are derived to be proportional to the virial radius, where proportionality is with the spin parameter, either the halo or the gaseous component, depending on how you want to model it. And the spin parameter parameterizes a specific angular momentum. And there is a prefactor for the unity that depends on the model, but roughly the sizes are expected to be proportional to the virial radius. And right there, it gives us a basic framework to understand why galaxy sizes get smaller, because as we go up in redshift, the halo mass goes down, because typically we deal with smaller and smaller galaxies. But even if you want to consider a galaxy with the same halo mass, even in that case, we expect 1 plus z evolution, right, just because the universe gets denser at high redshifts and the virial radii gets smaller, and therefore, if this holds, the sizes should get smaller as well, right? So this gives us a basic framework, but it may be too simple, right? So the question, does it work or not? And it turned out it does work, and it's borne out both by observations and models. I'll show you a random model from the literature. The work that we did with Oscar Gertz in 2016. And it also borne out by observations, as these points and shaded bands are redshift 0 galaxies for which the sizes are compared to the virial radius, where virial radius is derived from halo mass, shown here, and the halo mass is derived using stellar mass, using abundance matching, which by now I don't need probably to explain because it's pretty standard. But if you do that, you'll derive that sizes are roughly linearly correlated with size. This hides a lot of detail, but on average this holds. And these three lines here are three models which simulate the same galaxy with different star formation and feedback choices. For one of these, feedback is weak and the size just stays small. The galaxy ends up very incorrect and very compact. But for two other choices, when feedback is realistic and efficient, the galaxy evolves along this track that roughly tracks linear relation between size and virial radius. And depending on what we assume about the strength of feedback, if feedback is cranked up, unlike this blue case, which forms a very nice disk galaxy, in this case, the galaxy is very puffed up, and it's not actually a disk, it's a spheroid. But even in this case, the galaxy still tracks roughly linear relation, just with a different amplitude. Right? So this basic assumption that is postulated in classical models for galaxy sizes does seem to work when feedback is efficient. And this has been seen in a number of studies. This is one recent one from Karmakar et al. And it shows, again, the size, the effective radius relative to the virial radius of the halo, R200, as a function of stellar mass. And you can see that these relations for different stellar mass are pretty flat, which means that the size is roughly proportional to the virial radius. But the normalization does depend on implementation of physics, which is different. This is for two simulations which have different implementation of star formation and feedback, and they have somewhat different amplitudes, right? So again, there is dependence on implementation, but overall, the size is roughly proportional to the virial radius. Okay. So there are complications. There are also studies that show that this simple picture has problems because it expects that galaxy size is proportional to the spin parameter, and if you actually try to check whether this is true in simulations of galaxy formation, you find that there is some correlation, but it's not as strong as expected. These lines are linear relation. These points show what actually is measured, and it's considerably weaker, and has been seen in a number of different studies. Additional correlations were found with concentration, correlation with mass accretion rate, and so on. So overall, if you start looking into detail, this picture has deficiencies, right? It's not as simple as just angular momentum setting the size. There's more things going on. There is assembly history that matters, and the physics of both halo formation and galaxy formation. But on average, again, in ballpark, if we want to just have a crude framework, it does seem to work. And it is been checked in observations as well. So this is the half-light radius as a function of virial radius, at redshift from 0 to 3, now using HST observations. And there were two studies by Huang et al. And Rachel a few years ago. And they show that for both star-forming galaxies and quiescent galaxies, the galaxies exhibit roughly a linear relation with the virial radius, with a constant of proportionality of a couple, 2–4%, right? So roughly what is expected from these models. And with HST, this was extended to redshift 9, which also showed that galaxies kind of follow this, are consistent with the constant ratio between size and the virial radius, right? Okay. Does this work beyond redshift 10, right? So this is the frontier. And when I was coming to this workshop, I didn't know the answer. So I was actually working to compute it myself. And then I learned that Rachel has already done this. So I'm going to show you her results, which she kindly shared with us. What you see here is the size in physical kiloparsec as a function of absolute luminosities of galaxies with a collection of recent measurements from the literature, from JWST, for galaxies beyond redshift 10. And on top of it, there are some lines and there are points. So these points are model halos, for which it's assumed that the galaxies of a given luminosity live in a halo of particular mass using abundance matching again, just one-to-one, no scatter whatsoever. This places galaxies of a given luminosity into halos of the largest possible mass, right? So it's a procedure that makes this assumption that there's no scatter. And then for a given halo mass, you know what the virial radius is. And you can either assume that the size is proportional to the spin, to the virial radius with the spin factor. This gives this blue line, or just a constant 0.03. This is these points. And you can see that they roughly match observed sizes, right? So again, this type of proportionality seems to work, right? So it's all seems to fit together, except this model assumes that there is no scatter between UV luminosity and halo mass. And as we heard repeatedly, and if you read papers, you probably read many papers on the fact that star formation at high redshifts can be stochastic, and that may have a lot to do with UV luminosity function evolution at high redshifts. And so assumption that there is no scatter between UV luminosity and halo mass is unlikely to be realistic at these redshift, and so at least some scatter needs to be introduced. If the scatter is introduced, right, what it means is that now you'll be putting halos, galaxies of a given luminosity in smaller halos, so smaller virial radii, and the same factor will not give you observed sizes. The factor needs to be larger for smaller sizes to match the observed sizes. And the question, is it actually happening in simulations that show a lot of stochasticity? And the answer, interestingly, is yes. So this is Jason Sun's simulation that he talked about today, earlier today, but also he gave a seminar at the workshop a couple of weeks ago, which you can find online and listen at this link. After his talk, I asked Jason to give me the plot of the ratio of the virial radius to the half mass radius of stars in these high redshift galaxies in their simulation, the FIRE2 simulation. These are high redshift zoom-ins that were presented in my et al. And Sun et al. And lo and behold, when he sent me this plot, you can see that the ratio of the half-light radius and the virial radius is actually 10%, right, not 3%. So in this simulation, there's a lot of stochasticity between halo mass and luminosity. So the galaxies, the bright galaxies on average, actually small mass halos just been upscattered in luminosity. We heard discussion about this possibility earlier today. And in this case, you need higher star formation to happen, and stars being distributed in higher fraction of the virial radius, and that's indeed what they see in these simulations. So Jason earlier today, and again in this talk as well, he showed the actual distribution of star formation. This is greenish regions here that occurs over a significant fraction of the virial radius shown by circles in these galaxies, because at high redshift they're very, very turbulent, very, very chaotic, both due to very strong accretion of gas along filaments that just free falls into the galaxy, and also strong winds that are blowing out the gas from the galaxy that are so small. These are small dwarfish galaxies, right? The observations only are reaching somewhere around here, right? These are not really even observed yet, but these are all very small galaxies living in small shallow potential wells, so their blowouts happen easily. Right, so the picture where sizes are small, like couple of percent of the virial radius, may be actually changing during early stages of evolution, where star formation proceeds over a much larger fraction of the virial radius. This is at least what these simulations, and actually also some other simulations, are implying. In fact, if we look at the simulations that didn't phrase it this way in terms of virial radius, but just as the intrinsic actual absolute size of the galaxies is in physical kiloparsec as a function of stellar mass, redshift 5 to 7, redshift 7 to 9. This is from a recent paper by Jacob Shen et al., combining nicely very different simulations, so making my job much easier, because this is a mini review on its own. And what you can see here is that simulation results, there are some differences, but overall they more or less trace the same trend of size with stellar mass. And let me first point out the small masses, so dwarfish masses here. Look at the sizes, right? The sizes are for the kiloparsecs, right? It's not huge, but if you think about what the virial radius is expected to be for the halos of those redshifts, it's just few kiloparsecs, right? So when you see a half mass radius for the stars of about kiloparsecs, that's a very large fraction of the virial radius, right? So in these simulations, the stars also are forming over a significant fraction of the virial radius of those redshifts. Now, for more massive galaxies, there is a decrease. You can see that there is a turnover, and it's been seen in a number of different simulations, as you can see here. And this seems to be very different from what is observed. Observations are indicating that there's a lot of scatter, but some positive correlation, whereas here it's clearly negative. In fact, this has been discussed in the simulation papers, and it's been pointed out that this would be inconsistent, but maybe effects of dust are changing things. And so when they take a dust effect into account, which are uncertain, but nevertheless could be modeled, the effects seem to be significant. And when dust is taken into account, shown by these red points compared to the blue, when dust is not accounted for, the correlation becomes at least flat. It doesn't become positive, but becomes at least flat. But again, if you start comparing with observations, you can see that the space of observed galaxies is much wider. It spans towards lower sizes, much smaller sizes compared to the simulations. And that remains the question, with the simulations actually lacking very compact galaxies or not, in which case there would be some physics missing, or maybe observations are underestimating galaxy sizes. And I'm looking forward to Arjun's talk later in the session to hear what he has to say about that. Right. So the things are quite uncertain, but I think, again, it's not very controversial that high redshift galaxies are smaller than galaxies at low redshift. The implications of this are profound, I think, because smaller sizes for similar gas masses and stellar masses, and from models we expect that galaxies are gas rich at those redshifts. We expect that if you plug in a typical number, say gas mass of 10 to the 10, size of half a kiloparsec, you get effective surface density within half-light radius or half-mass radius of 6 times 10 to the 3. That number may not mean much to you, but if you start comparing it to densities of various systems, you find that it's actually comparable to density of globular clusters, which is some of the densest objects that we know in nearby universe, right? So these are very dense environments, and we're talking about average density of the interstellar medium, not some, like high density region. It's an average, right? So when you have such an average, it means that fluctuations from that average can lead you to very high densities. And so this may help to explain why, when we model spectra, we constantly derive densities that are very high, right? So these high redshift galaxies, the average density of interstellar medium can be very high. And when you introduce turbulence and you introduce fluctuations around this mean, the high density tail of those fluctuations may reach into very high densities indeed. And one of the things that may be implying by these high mean densities of interstellar medium due to small sizes is that such environments can be conducive to different regime of star formation, in which most of the stars are forming in massive, dense, compact clusters. We see direct evidence of this in JWST imaging now, right? This is a galaxy at redshift 10.2. This is a background galaxy. Both of them are lensed. But this galaxy, which the authors named Cosmic Gems, is a nice galaxy with clearly distinct clumps at high resolution in one of the bands. Sorry. You can clearly see different clumps with lensing. You never know whether it's the same thing multiply imaged or not, but these authors did lensing analysis and showed that it's actually 5 distinct clumps. And then resolved, they have sizes of only a few parsecs. And if the lens source plane reconstruction is done, there is these 5 clumps that are just few parsecs in size. But the remarkable thing is that those clumps contain 60% of UV light, which means that 60% of star formation is occurring in those dense clumps. Their masses and densities are higher than typical globular cluster in the Milky Way today. So we truly are seeing very massive compact clusters forming in the system, and most of the star formation is proceeding in these clusters. A similar system was published by Movla et al. Earlier this year, somewhat smaller mass, consistent with being Milky Way progenitor. But again, when the lens and reconstruction of this object is done in the source plane, the UV light distribution has some diffuse component, but about 50% of the light is in several massive and compact few parsec scale clusters. So we start seeing this in more and more objects. And one of those objects we actually saw that even before these papers came out was Milky Way. The evidence here is not direct. We cannot image Milky Way the same way as we can do these high redshift galaxies. But in the Milky Way, there's strong and direct evidence that early stages of its formation were accompanied by a similar regime in which most of stars formed in massive compact clusters. What you see here is analysis from the paper I did with Vasily Belakura, where a fraction of stars that are high in nitrogen abundance, so with nitrogen to oxygen ratios about 0.55. These are numbers for people who don't think about these things. These are numbers similar to what people are measuring from the spectra of high redshift galaxies in terms of nitrogen abundance. But in the Milky Way, those type of nitrogen abundances are observed for stars in massive globular clusters, right? These stars here, this fraction is for the field stars, not the stars of globular clusters. These are field stars. And the field stars that are classified as in situ, I won't go into detail how we do it, ask me afterwards if you're interested. But these are stars that were born in the progenitor of the Milky Way. And what you can see is that the fraction of such stars increases rapidly with decreasing metallicity, reaching pretty high values of like few percent. And if you take how many clusters would it take to produce such fraction of high nitrogen to oxygen stars, you'll find that about 50% of stars should have been born in massive means 10 to the 6 solar masses, globular clusters, when these stars were born, right? So it's evidence that Milky Way went through a similar stage of clustered star formation, similar to what we see through direct imaging of JWST. Now, what are the implications? There are many interesting implications of this, so I encourage you to talk about this and to think about this. This is another galaxy from Seiji Fujimoto, Cosmic Grapes. there's more and more examples of such systems. This is redshift 6, again, large fraction of UV light in these clumps. And the implication of this type of star formation is that there's something that was already mentioned, that the high nitrogen abundances, this may have something to do with it if this is widespread. The high Z star formation may be traced by globular clusters. You can ask what's the big deal. Well, we don't know. We know that overall star formation galaxies over the entire Hubble time is not traced by globular clusters, simply because, say, metallicity distribution is very different. But the high redshift star formation may be traced by globular clusters, in which case surviving globular clusters gives us a probe of that early regime of star formation. Then what is interesting, I think, is something that emerged during discussion in this workshop, is that black hole remnants of massive stars that form in these clusters, and these remnants can be quite abundant because dense environments of these massive clusters can be conducive to stellar collisions, forming massive or even supermassive stars that explode and leave supernovae behind. While if this happens while cluster is still forming, when there's lots of gas, those black holes can emit X-rays in UV and contribute non-trivially to the spectrum of the galaxy. Large fraction of black holes in those early clusters can also provide seeds of black holes. And what's particularly intriguing is that the star cluster around those black holes may be helping to pin down the black hole and not allow it to wander around the galaxy, something that people found happened quite easily in simulations. So they may help to both seed the black hole and keep it pinned to the center of the galaxy. So there are many, this is just a sample, there are many potential implications of this new regime, but I want to use the remaining few minutes to say a few words about morphology. So what about morphology? Well, here's morphology, this example of morphology in simulations. Qualitatively, it's very consistent with what we see. It's very complex, very clumpy, very elongated. So qualitatively similar to what observed galaxies high redshift look like, but you can ask the question, where are the disks, right? And these massive simulations do not produce disks, but in the observation, I didn't mention this, but in this case, the gas measurements indicate that this is a rotating disk. So the question is, do simulations actually produce disks of those high redshifts? And the answer is yes, they do. But they expect that the disk should be prevalent in high mass objects. So this is a figure from Annalisa Pilepich's work based on illustrious CMG simulation, which shows a fraction of star-forming galaxies as a function of redshift that are in spheroidal, elongated, and disky systems. And you can see that for stellar masses of 10 to the 9 to a few times 10 to the 9, at high redshifts, the disk fraction is expected to be very small, but as you go up in stellar mass, the disks are expected to be prevalent. So you do expect disks, but they're expected to be massive, right? So no low mass disk. In fact, the star formation, the galaxy formation model indicate that the galaxies start to form disks when their stellar masses reach 1 billion solar masses, roughly. Very roughly, but something like this. In fact, for the Milky Way, we see some evidence that this is indeed what happened. The Milky Way disk formed when its progenitor reached a mass of about 1 billion solar masses. The physics of disk formation is still being debated. This was a subject of dozens of papers over the last few years. I just mentioned a few of them here. And it's still not been conclusively agreed on what is the physics of disk formation. But what we can see is that in simulations, there is always a stage of evolution before disk forms. When the distribution of gas and stars is very chaotic, when stars are forming over a significant fraction of the virial radius, and then the disk forms at some point, and that point is usually accompanied by formation of a hot halo, by mass reaching a particular value of about 10 to the 11, stellar mass reaching about 1 billion solar masses, but it hasn't been proven exactly what process allows the disk to form when it couldn't form before. So given the lack of time, I will skip what I wanted to say about the formation of the Milky Way disk. So the evidence that disk in the Milky Way formed roughly at redshift 3 to 5, so maybe even in the first billion years. Ask me afterwards if you're interested in, and I'll leave you with, oops, this is, I want to skip, so I'll leave you with my summary about the sizes. So galaxies at high redshifts are smaller, and roughly, we still have a lot to do to understand exactly what sets the sizes, but roughly it follows, this trend follows what we expect. Observational model results in size luminosity planes seem to be quite at odds with each other, and it's not completely clear to me which ones are to blame, whether the models are completely wrong or observations have issues. It's something that would be interesting to discuss after the talks in the other talks in this session. The smaller sizes, redshift 5, imply that these galaxies, given that they have normal stellar mass and are expected to be gas-rich, should have very high mean densities of interstellar medium. Such high densities can lead to unusual spectra and very unusual mode of star formation, whereby most of stars are forming in massive, compact globular clusters. And models and Milky Way observation as well indicate that galaxies undergo a chaotic early stage, turbulent stage of evolution when this does not exist. This form at some point, and we see evidence in simulation, we clearly see this happening, and we see evidence in the Milky Way, something I have to skip, but ask me afterwards, that such stage existed and the disk formed at some point, but the exact physics of this formation is still being debated. Thank you.
Nice review, Andrey. Can two people just man the mics on either side? Lots of questions. Start with Erica.
Okay, I have a question about the how the effective radii of the galaxies are related to the effective radii, the virial radii. So Avishai tells us that like there's all these compaction events and stuff, and this drives the sizes of galaxies. So how, I guess I don't understand why physically those two things would be so strongly correlated.
So I'll give my view, and then maybe Avishai can comment. So I think compaction may be happening in some galaxies, and that contributes to the overall scatter. What I would argue is that it doesn't happen for most galaxies, so on average, galaxies still maintain this relation. I showed one of the first slides, I showed that in a simulation where feedback is inefficient, the galaxy does become compact, and then virial radius doesn't correlate with, the size doesn't correlate with virial radius. It's when feedback is efficient, is when the gas is able to preserve specific angular momentum, and the size seems to track the simple picture. Alicia, do you want to add?
I don't think you really need compaction events for the small sizes that we're talking about here, because the high redshift, the virial radius itself is so small, it's only 10 kpc or less, that if you multiply by the spin parameter, you get very small sizes, so almost automatically. Compaction event can help you by another factor of 2 or so, but it doesn't make a huge qualitative difference, I think.
Thanks, Andrey. Superb talk. Not that I'm biased, because of course I love this topic. So this inverted size-mass relation that we're seeing in the simulations is really interesting. And at lower redshift, it's been shown by Daniel Alcazar, Rachel Cochran, and also independently by Ina Choi, that AGN feedback can also prevent this overcooling in the centers of massive galaxies and give you, the size-mass relation that we're more accustomed to. Now, we're not used to thinking that AGN feedback is important at these redshifts, but it may well be. I mean, several of those simulations don't have black holes, right? Fire 2, and I don't think Sarah has black holes, right? And it may be that in Tisan, blue tides, maybe the AGN feedback is 2 weak. So I'm just putting out there, what do you think, that maybe this could be impacted by AGN feedback if indeed black holes are common at these redshifts? So
I did read the papers. I tried to see whether they actually would invoke AGN feedback in any way. So most of these lines actually are simulations that do include AGN feedback. So Simba, the flares, I believe, included definitely the sun and TNG. And it's only this Simba that sort of shows something that may be rising, but still the sizes overall seem to be consistent with our simulations. So they all include feedback in different ways, and they all seem to be getting the results that roughly similar.
But the AGN feedback is really, really weak at these redshifts in all of those simulations.
Okay.
I mean, this is maybe a longer discussion.
Maybe that's a common problem, I don't know, but that's a good topic to discussion. I'm not sure I know the answer. I can tell you that these authors of this paper and also other papers, they try to, rather than to explain it with the AGN feedback issues, they try to explain it with the dust effect.
Alice?
Okay, thanks. That was great. I have a really sort of basic question. Just the observational size that you're using to compare with the models. It seems like most of the things you're quoting are the rest UV size. Now, it would seem to me that something more physical in terms of like tracing the starlight would be like the rest optical size. And I know there's a paper by Ono et al. That looks at the ratio of the rest optical to rest UV size. They're similar, but they're not the same. So I guess I was wondering why you're consistently using the rest UV size, which seems like it could be more susceptible to, you know, dust extinction, you know, effects than something at longer wavelengths, which you can do now with JWST.
Right, but majority of, I believe the majority of sizes published, like for largest samples, still UV sizes. And I think it would be nice to have it compare it larger. But in models, it's possible to just directly give UV sizes, and it's been done. These papers, like in the second plot that I was showing, it actually was showing UV sizes with and without dust, right? It's a dust is the major uncertainty, not the fact that you can always forward model UV. But my impression was that this redshift above 5 galaxies, definitely redshift above 7, these galaxies are still in a fast accretion mode. So most of their stars are fairly young. And so, like, for example, here you can see this is UV, this column, this is, no, sorry, this is actual star, I think this is stellar mass, this is UV, and this is B band. And if you look at, for the same galaxy, they're not that different, right?
Sure,
so,
sure.
And that's, I think, is because most of the stars are young, right? So there are some factors, some differences, but I think on the scale of discrepancies and the issues and the scatters that we're considering right now, those differences are relatively small. That's why I thought it would be okay to sweep it under the rug. Plus 25 minutes would, you know.
Thanks.
Yeah, also I'd like to congratulate him. Nice talk, Andrey. Concerning the disks, I think that there are also two other factors we have to keep in mind. First of all, that disk form relatively early. We see already disk at redshift at least 7, and these disks not only are there, but they're, I think, in intermittent nature. So they are there, then they are destroyed by mergers, then they reform. So it's a very dynamic process. That's one first point. The second point is that, surprisingly, these high redshift disks are extremely thin and cold. And so that means that the feedback cannot, which you pointed out that weak feedback allows the formation of disks, or at least feedback in the right, at the right amount of feedback. And so this cold disk could mean that the feedback is also weak. So everything comes together, I think, right? So yeah. What do you think?
Well, a couple of things. So one is that I tried to make this point, so I'm going to try to make it again. So the disks, at least in this simulation, last changes simulation, the disks are expected to be prevalent among star-forming galaxies at high redshifts for massive galaxies, right? So it's the low mass galaxies where they're expected to be very few. And that's because of feedback, because the low mass galaxies are susceptible to puffing up of the gas and stars by feedback, right? Massive galaxies are not so susceptible, and so they should have a lot of thin disks. And these are stellar disks. You're talking about gaseous disks. Gaseous disks are even easier to make, right? So that's one. But having said that, there is a lot of uncertainty in simulations about when exactly the disks form. And that's also because formation of a disk and survival of a thin disk is sensitive to the strength of feedback. If the feedback is too strong, you may never form a disk. You're just going to form a puffy thing. That's what happened in the simulation I did with Oscar Agertz at the time. So you crank up the feedback, and when with normal fiducial feedback disk forms, you just end up with a very puffy, diffuse thing. The same thing can happen at high redshifts, and one thing that I didn't show is that Milky Way size simulation have been struggling to reproduce formation of the Milky Way disk because they tend to form disks later than the Milky Way forms. One anecdotal unpublished result is that a resimulation of one of the illustrious TNG disks that one of the earliest forming disks, and in that case in TNG it formed at redshift 4. A simulation with a different code, with a different feedback, which produces also realistic result, shifted disk formation for the same initial condition to redshift 7. So there's still quite a bit of uncertainty within the simulations about when exactly, even for the same initial condition, disk forms. And I view this as a feature, not a bug. You can say, well, simulations are uncertain. Yes, they are when it comes to star formation feedback, but this sensitivity means that observation can help us to understand what feedback levels are realistic at those high redshifts. There's also merging, there is accretion, right? So it's all together. But I think the feedback here plays a key role because we know that without feedback, things don't happen right? So we know that we need feedback to form galaxies, realistic galaxies at low redshifts, but we don't know whether current simulations have feedback that is too strong at high redshifts. And that has a lot of bearing on a lot of different things, including stochasticity of star formation and all kinds of issues, metallicities and so on.
redshift 4 and redshift 7, was there significant differences in the dark matter, in the shape of the dark matter potential?
I don't know, but it's a good question.
Thanks for a very nice talk, Priya. So I have a related question. So in the very high Z disk formation, are the properties, the spin parameter of the dark matter halo, is that relevant or is that irrelevant? It should be relevant, right? Do you, when you said, do they form, the gassy disks form and then the stellar disk forms, does that depend on the spin parameter? Like when you talk about where does it form, is it preferentially lower spin halos? Has that been looked at? Are these?
No, I'm not sure. Usually you see disks, the size of the disk does correlate to the spin parameter.
Right.
Not as perfectly as linear, but there is a correlation. But I do not...
in terms of the sites, right? Which
yes, I don't recall spin being explored as a trigger for the earliest disk formation.
I see.
What I was trying to convey is that the timing of the disk formation seems to be related quite strongly to how strong the feedback is, because it is a feedback that prevents early disk formation in small mass halos. And therefore, if feedback is too strong, the disk formation is delayed. If it's weaker, then the disk formation is earlier. So that is...
Just wondered if there was this hidden parameter.
There may be,
the spin.
yeah, but I would guess that it's a secondary parameter compared to feedback.
Can the next speaker come up and then we'll just take one last question?
So just as a follow-up from Rachel's question, so if you go back to the plot where you showed the different simulations for the mass isolation, so like basically the SIMBA simulation had a positive correlation and the other simulations had a negative correlation. I was wondering if it's something to do with the accretion model in SIMBA being different, with the gravitational torque-driven model being used instead of the Bondi accretions for the other simulations. It could mean maybe higher accretion rates and a higher, stronger feedback for the SIMBA at higher redshifts compared to the other simulations.
Yeah, so my answer is I don't know. I think it is true that SIMBA does have a different model of AGN accretion, right? So that may have something to do with it. But to me, given the dynamic range here, yes, it looks somewhat different, but look, like there's a significant region of overlap as well, right? So overall, I wouldn't make too much of a, we don't know how many objects, for example, are here. So I don't know how much to make of it.
Thank you.
Let's thank Andrey once again.
Right.